Welcome back to AI.Code.Cast. It's our little corner of the deep dive where we get to, really dig into some cool coding challenges.
Yeah.
And today we're looking at the remove duplicate letters problem.
Fun one.
It is. Yeah, it's over on LeetCode if you want to check it out yourself.
Yeah, one of the classics.
It is one of the classics, and it's a good one to kind of wrap your head around, I think.
For sure.
So imagine you have a string of letters,
Okay.
like BKBD,
Mm-hmm.
but some are repeated.
Mm-hmm.
The goal is to find the smallest possible substring that contains all of the unique letters, so no duplicates.
Right.
So for BKBC, the answer would be ABC.
Okay, so what's interesting here is smallest doesn't just refer to the length of the substring.
Okay.
Like, we're not just trying to find the shortest one.
Gotcha.
We're talking about something called lexicographical order.
Lexicographical order.
Yeah, and you can think about it like alphabetizing words in a dictionary.
Okay, so we're aiming for like alphabetical efficiency.
Exactly.
Okay.
Yeah.
I like it. So let's look at another example here from our source material. We have the string CBCDBC.
Okay.
What would be the smallest substring in that case?
So for CBAC-DCBC, the smallest substring would be ACDB.
SEDB, yeah.
Yeah, because if you were to arrange all the unique letters alphabetically, ACDB would come first.
Okay, so like SEDB beats out every other combination of those letters in like a dictionary sorting contest.
Exactly. Yeah.
I like it. Okay, so how do we actually even go about finding these smallest substrings?
So one way to do this is to just try every single combination
Ah.
of the unique letters and see which one comes first alphabetically.
Right, so just like try everything.
Yeah, this is like the brute force approach.
Brute force, okay, so very straightforward, very, basic in terms of its logic, but I imagine that could get kind of crazy,
Oh, yeah, for sure.
especially with longer strings.
Brute force is like the easy solution to think of, but it can be super time consuming.
Okay.
Like, imagine a string with 20 letters.
Oh my gosh.
The number of possible combinations would be enormous.
Yeah, that's a lot of combinations.
It's just not very efficient.
So brute force is out. What's a smarter way to approach this? Are there any hints in our source material?
So our source material mentions this idea of a greedy algorithm.
Okay.
And using a stack data structure.
A stack.
Yeah.
Okay, those are some pretty significant clues.
Yeah, for sure.
Can you unpack those concepts for us? What makes this algorithm greedy?
So a greedy algorithm basically just focuses on making like the best local choice at each step
Okay.
without worrying about like the long-term consequences.
So you're not thinking ahead too much. You're just like, what's the best right now?
Exactly. Yeah, you can think about it like if you're at a buffet,
Yep.
you're grabbing the tastiest looking appetizer
Yeah.
without considering if you'll have room for the main course.
Yeah, I like that analogy. I often fall into that trap at buffets.
Yeah.
But how does that apply to finding the smallest substring?
So you can think about it like building a tower brick by brick.
Okay.
So each letter in our string is like a brick. We want the smallest tower possible,
Gotcha.
and we're going to use a stack to help us build it in that greedy way.
So the stack is like our construction site in this case.
Exactly. Yeah.
Okay, so how do we use it to make the best choices as we're going?
So imagine we're going through our string letter by letter.
Okay.
At each step, we decide whether to add the current letter to our stack tower or not.
Okay.
And we want to prioritize smaller letters because they come earlier in the alphabet.
Right, so like A before B, that kind of thing.
Exactly. Yeah?
Okay, but what if we encounter a larger letter that we know we need later for our unique set?
Right.
Do we just, like, discard it?
So that's where the greedy part gets a little bit tricky.
Okay.
We need a way to keep track of whether we've seen the last occurrence of a particular letter in the string.
Oh, so we don't accidentally throw one out that we haven't seen the last of.
Exactly.
So we need some way to look ahead, I guess.
Yeah, and our source material mentions something called a last occurrence map.
Okay, a map.
Yeah.
What is that?
So basically this map tells us the index of the last occurrence of each character in the string.
So, like, before we even start building our stack tower,
Mm-hmm.
we kind of do a reconnaissance mission through the string and just, like, map out where each letter last appears.
Exactly,
Yeah,
yeah.
okay.
And that's going to help us make these decisions.
Well, that's our secret weapon.
Yeah.
I like it. Okay, so this is getting very strategic.
Yeah.
I'm starting to see how this greedy approach with a stack in this last occurrence map could lead to a pretty elegant solution.
For sure.
But how do we actually put all these pieces together
Sure.
to actually, like, build our substring?
Right, so let's kind of break down the steps of the algorithm.
Okay, great. Let's get into the nitty-gritty. How does this work?
So first we create the last occurrence map.
Right.
It's go through the entire string, and for each character, we note down like, okay, this is the last time it appears.
Yeah.
So for like BCAG,
Right.
the last occurrence of B would be at like index 3.
Okay.
C would be at index 4.
Oh.
A would be at index 2, and so on.
Okay, so we got our map ready to go.
Yep.
Now we start building the substring with our stack.
Exactly. So now we iterate through the string again,
Good.
this time like letter by letter.
All right.
And we're going to use our greedy strategy
Okay.
and that last occurrence map to make decisions.
So let's take our example BKBC and walk through it step by step.
Yeah.
So we encounter the first letter B.
Okay.
What happens?
So our stack is initially empty,
Right.
so we just push B onto it.
Okay, no need to check the map or anything yet.
Not yet.
Okay, cool. So next letter, C.
All right, so now this is where the map comes in handy.
Okay.
So C is like lexicographically larger than B,
Right.
which is already on our stack.
Mm-hmm.
But before we just like push C on there,
Yeah.
we're going to consult our last occurrence map.
Let me guess. We want to see if we have another B coming up
You got it.
later in the string.
Yeah.
Because if there is, we might want to hold off on C.
Exactly. So we look at our map and we see, okay, the last occurrence of B is at index 3, which is after our current position.
Right.
So we can't pop B off the stack just yet.
We got to keep it around.
We got to keep it around.
Okay.
So we push C onto the stack as well.
Even though it's larger than B.
Exactly.
Okay.
So at this point, our stack has B on the bottom and C on top.
Right.
It might seem kind of counterintuitive to add a larger letter on top of a smaller one.
Right.
But remember, we're playing the long game here.
Okay. I'm trusting the process.
Yeah.
Okay.
So next letter, A.
All right. This is where it gets really interesting.
Yeah, this is where things get spicy.
Yeah. So A is smaller than both B and C.
Right.
Which are currently on our stack. So now we need to be strategic.
So back to the map.
Back to the map.
Okay.
We see that the last occurrence of C is at index 4.
Okay.
And the last occurrence of B is at index 3. Both of those are after our current position.
So we can safely pop both C and B off.
Because we know they'll come up again later.
Exactly. We want to prioritize that smaller letter A
Right.
to get that smallest substring lexicographically.
Okay.
So we pop B and we push A onto the stack.
Okay, so now the stack only has A.
Exactly.
Okay, I see how we're using the map to like make these strategic pops.
Yep.
It's like we're carefully like rearranging the letters to get the smallest ones at the beginning.
That's a great way to think about it.
Okay, so next letter, we encounter B again.
Okay.
So B is larger than A, but we know we need it in our final substring.
Right.
So we just push it on the stack.
Exactly. So now we have A at the bottom and B on top.
Got it. And finally, last letter, C.
So C is larger than B.
Right.
And we see that the last occurrence of C is at our current position index 4.
Okay.
So we can safely push C onto the stack.
Okay, so we've reached the end of our string.
Yep.
And our stack contains the letters A, B, and C.
Exactly.
In that order.
In that order. So to get our final substring, we just pop the elements off the stack in reverse order.
Yeah.
And voila, we have ABC.
There it is.
Yeah.
Okay, this step-by-step walkthrough makes it so much clearer. It's amazing how we're essentially using the stack to like temporarily hold letters.
Yeah.
And rearrange them to get that optimal like lexicographical order.
It is quite elegant.
It is.
Yeah.
Speaking of efficiency though,
Okay.
what is the like time complexity of this solution?
Right.
Because we're going through the string a couple of times. First to create the map.
Yeah.
And then to like build the substring.
You're right. We do iterate through the string twice.
Right.
But in terms of big O notation, the complexity is still considered like linear
That's
O of
okay.
n, where n is the length of the string.
No.
Because the number of operations we do grows proportionally to the length of the string.
So even though we have multiple loops, it doesn't like drastically increase the time it takes to run.
Exactly. Yeah.
Okay, what about space complexity? We're using a stack and a map to store information. How much extra space are we using?
So both the stack and the last occurrence map will at most hold one entry for each unique character in our string. So the space complexity is also considered to be linear.
Okay.
O of n.
So this greedy algorithm with a stack is not only elegant, but it's also pretty efficient.
Yeah.
In terms of both time and space.
For sure.
That's impressive.
Yeah.
Are there any potential pitfalls with this approach, though? What if? What if we had a string with like uppercase letters or even special characters? Would this approach still work?
That's a really good question. So our current implementation kind of relies on the fact that we're dealing with lowercase English letters.
Okay.
If we had uppercase letters or special characters, we'd need to adjust our last occurrence map accordingly.
So the algorithm itself is adaptable.
Yeah.
We just need to be mindful of the types of characters we're dealing with.
Exactly. Yeah, the core logic of the algorithm remains the same. But the implementation details might need a little tweaking.
Got it.
Depending on the specifics of the problem.
Are there any other limitations we should keep in mind with this greedy approach?
So remember that this specific algorithm is designed to find the smallest substring.
Right.
Lexicographically. If the problem was to find, say, the shortest substring with all unique characters, this approach might not give us the optimal solution.
So it's a powerful tool.
Yeah.
But it's important to use the right tool for the right job.
Exactly. Understanding the problem constraints thoroughly is crucial before diving into any solution.
Okay, that's an important takeaway.
Yeah.
I think sometimes it's easy to get caught up in the excitement
for sure
of a clever algorithm and forget to consider the big picture.
Yeah, it's always good to take a step back and make sure that the approach you're choosing really aligns with what the problem is asking.
Well, this deep dive into remove duplicate letters has been really insightful, I think.
Yeah, it's a fun one.
We've explored the problem, the limitations of brute force, and then this elegance of the greedy algorithm with a stack.
And we've seen how a simple data structure, like a stack, combined with a strategic approach and a little bit of mapping, can lead to a surprisingly efficient and elegant solution.
Definitely. It's a great example of how algorithmic thinking can really break down a seemingly complex problem into these manageable steps.
For sure. And it highlights how understanding these underlying principles allows you to adapt and apply these techniques to other coding challenges as well.
It's all about the fundamentals.
Exactly.
Awesome. Well, this has been a fantastic exploration. But before we wrap up, is there anything else that you want to leave our listeners pondering, any final challenges to spark their curiosity?
So we've focused on finding the smallest possible substring in lexicographical order. What if we flipped the script?
Okay.
How would you modify this algorithm to find the largest possible substring while still ensuring all unique characters are present?
That's a good one. So it seems like we would need to reverse our thinking about, like, smaller and larger when we're making our decisions with the stack.
You're on the right track.
Okay.
Instead of prioritizing smaller letters, we need to prioritize larger ones.
Gotcha.
Think about how that would change our stack manipulation logic.
That's a great challenge to leave our listeners with. It's fascinating how just like a minor change in the problem statement can lead to like a significant shift in our approach.
Exactly. It emphasizes the importance of really thoroughly understanding problem requirements.
Yes.
And being adaptable in your coding approach.
Absolutely. Well, thanks for joining us on this deep dive into the world of algorithms. Until next time, happy coding.